Welcome back, everyone, to the Python tutorial seminar series. Today, Anissa Zacharias will be covering plotting with GeoCAT. This session will cover some advanced plotting techniques and customization and highlight some of the functionality that has been developed by the GeoCAT team. We're really excited to share this with you, and we hope that you find it useful. Before we begin, we have to review the code of conduct. By joining this Zoom call, you've agreed to adopt these values and engage in respectful communication. Any inappropriate remarks will have you removed from the call. The seminar is only 1 hour long, as usual, so if you need help, ask it in the chat and we will try to help you. If you do have a bigger problem than that, though, we might need to provide one-on-one assistance after to get you up to speed. And some useful resources for today, which I will post in the chat. As always, Stack Overflow is a great tool for figuring out how to solve specific problems that you may be having. The GeoCAT examples gallery has a plethora of plotting examples that you might find useful. And today's content is on Anissa's Plotting with GeoCAT tutorial GitHub repository, and I will post the link to that as well. And with that, I will pass the baton on to Anissa.
All right, let's see if I can share my screen. All right, I'm going to assume that's working unless I hear otherwise. So this is the advanced plotting with GeoCAT, GeoCAT examples, GeoCAT-Viz, and you. I am Anissa Zacharias. I'm a software engineer too on the GeoCAT team, and this is what we have for you today. So GeoCAT is the Geoscience Community Analysis Toolkit, which is a collection of tools related to transitioning NCL to Python. GeoCAT consists of two main components, a computational and a visualization component. The computational component will be the subject of next week's tutorial, or 2 weeks from now tutorial. But this tutorial will cover the visualization component of GeoCAT, GeoCAT-Viz, and GeoCAT examples. This is on the left or on the right, a link to the GeoCAT homepage where you can find everything you will need to navigate the GeoCAT project, including the contributors guide, links to our repositories, and monthly updates. So GeoCAT examples is a gallery of plotting examples, which you can find on the link to the right over here. This started as a hackathon that aimed to show that NCL plotting capabilities could be recreated in Python using packages like matplotlib and cartopy. Since then, the gallery has been continuously expanded by the work of our great SciParks interns in 2020 and 2021, and by members of the GeoCAT team itself. This gallery does in fact show that NCL's visualization capacity can be largely recreated with Python tools. But some of the aspects of exactly replicating NCL scripts add unnecessary bulk, complication, and sometimes aren't fully faithful to the original NCL. That is where GeoCAT-Viz comes in. GeoCAT-Viz was initially created as a place to house convenience functions to make NCL plots or Python recreations of NCL plots as clear and as close to their NCL counterparts as possible, and to reduce the bulk of lines required in GeoCAT example scripts. And this is the current state of the GeoCAT-Viz repository. We are currently in the process of expanding this repository to provide plotting examples that aren't so easily recreated in pure Python, such as Taylor diagrams and stuff that reduces the number of utility functions in bulk that you need to know about in order to recreate NCL style plots. All right, and that brings us to our demo. So in the chat, there should be a link to this repository. There are detailed instructions here about how to set it up, but we are going to go through it. And if you are on Windows or have any sort of trouble with the setup instructions below, you can hit this Launch Binder button, and it should create an environment for you that should work just fine for this tutorial. This might take a minute to run, but I won't be going too fast at first, so don't worry. So now, in my terminal, we're going to go through the setup instructions. This is setup instructions for a lot of these tutorials. We are going to clone the repository with git clone. and then the link that should be in chat. Oops. And then we're going to navigate into that with CD, and then it should be called Plotting with GeoCAT Tutorial. And then from in here, we're going to create the environment GeoCAT-Viz tutorial using the same methods that we have before with conda environment create file environment. I'm not going to do that because I already have the environment file, but it's pretty small. It shouldn't take that long. And then we're also going to activate the environment by doing conda activate GeoCAT-Viz tutorial. And then once you have all that done, you're going to want to run Jupyter Lab, which will launch the lab for you if you're not doing this with Binder. All right. So once we have that up, yours is going to pop you up right from here. And so we're going to navigate into the notebook section, and then we're going to launch the first notebook, which is our advanced plotting with GeoCAT examples. This notebook is going to cover one of our most popular examples in the GeoCAT repository, Animate 1, without worrying about the NCL style visuals or stuff that we did in the examples repository to make it run on Sphinx, which is how our gallery is hosted. Animation is a topic that is frequently useful, but a bit tricky to figure out the first time around, as some of my GeoCAT colleagues can tell you trying to get this example set up. And in the second notebook, which we're going to touch on after this one, we're going to be looking at plotting using current and future GeoCAT-Viz functionality, which we removed from this example. All right, so if you want, you can go see the original GeoCAT examples gallery. Say if you wanted to know how to do animation and you knew we had a GeoCAT examples repository, you could go to our homepage, which is here. The homepage of GeoCAT examples gallery, and you would click on animate, and that's where you would find this example. As I said in here, there's a lot of GeoCAT-Viz utility functions that we are going to be omitting for the first notebook, but we'll get into that later. So in case you ever want to find this, you can either find it hosted on this tutorial or in our example gallery. So back to the notebook. The prerequisites for this are the prerequisites for our first Matplotlib tutorial, which is familiar with NumPy, Matplotlib, CartoPy, and Xarray. Though you do not have to be overly familiar with CartoPy or Xarray in order to do this. So for our imports, it is very much the same, CartoPy, NumPy, Xarray, and Matplotlib. And for our GeoCAT specific imports, we're going to import GeoCAT data files, which is just something that we use to host files that are from the original NCL examples. So we can easily use them to recreate in Python. Note, the first time you use this, GeoCAT data files, I mean, and the first time you pull down a file, you will get a little warning box, but don't worry about it. It's just GeoCAT data files telling you that it's pulling down the registry of all available files and that it's downloading this onto your system. So you won't see that on mine because I've already used GeoCAT data files and I have this file. So here's how we get the data we want to animate. Here we're using GeoCAT data files and we're pulling down this file and we're pulling it in with Xarray, which will give us a Xarray data set. And from this data set, we're going to pull out the surface temperature data, or data array, which we're going to call TAS. So if we look at what we have here, we do have an Xarray data array, and it's a lat long grid over 31 time slices, which I believe is in January. So we have a lat long grid that we're going to plot, and then we're going to animate it over the 31 time slices. So let's just kind of have a look at what we have here. We're going to use Xarray directly, and we're going to call it on the first time slice. And we're going to call plot and then contour F on it, just like we would using Matplotlib, but we're going to call it directly off of our Xarray object. Also, I'm specifying levels here because if you do a reduced levels, it plots with like 5 levels by default, and it's just really hard to see what the data is doing. So I arbitrarily specified a higher number of levels. So if we run that, we see about what we think we're going to see. Xarray was nice and took care of a lot of the labels and X and Y ticks for us, and also made us a little color bar. You might be able to tell that these are some continents here, but it's all kind of fuzzy and blurry. And well, at least we know we have something that looks like data. That looks about right. So from here, let's go ahead and add the correct projection. So everything is smooshed out properly like the data expects, and a map overlay so that we can see exactly where the continent lines are. Let's change the axes a little bit to be more of what we're expecting, and the color map to be something more intuitive to temperature maybe, and change the size and positioning of this color bar, which is a holdover from NCL that I'm going to copy because I like it. All right, so here again, we're specifying a figure. You might have noticed I specified a figure up here when I didn't technically need to. This would have done it all by itself, and it would have just plotted out the axes. But here we actually do need to specify a figure, although it doesn't look like it right here. So we start off by making a figure, and then we explicitly set up the axes, which we didn't do before, with a plate curry projection. From here, on the axes, we call coastlines and the line widths. If I'm going a bit fast through this, it's because a lot of this was already covered in the Cartopy and Matplotlib tutorials. And you can definitely go back and look at those to kind of get a slower version of what's going on here. And again, we're going to plot the first time slice and roughly the same inputs, just as we did. We're giving it the axes, so we get the projection. We're giving it the same transform as the axes. Again, just specifying the levels. I'm going to use the Inferno color map because I like it for temperature things. And I'm going to give it some color bar coorgs, which will just move the color bar from up and down on the side to on the bottom, and I'm going to relabel it. And now I'm going to configure the axes. You may have noticed I said that Xarray took care of the X and Y axes for us up here. So every time I call this, it will in fact overwrite anything I've done with the axes and tick marks. So after I do this, I'm going to overwrite its overwrite and just stretch it out a little bit. So if we run that, that's about what we're seeing in the Xarray. In the GeoCAT gallery examples. And this looks like something that I want to animate. This is just the first time slice, but I would really like to see what all the other ones look like now. So animation using Matplotlib. We're going to be using Matplotlib's func animation, which makes animations using the progression of a function, which might sound confusing now, but we'll go over it better. Using this feature involves 3 steps. The first one is creating an initial state of the plot and making a function that can progress the animation, and finally calling func animate with those things that we have created. You can see Matplotlib's animation documentation for much more information and other ways of animating things that don't rely on functions. So we're going to import func animation real quick. And so for the first step, the initial state, we actually already did that. This is our perfectly configured initial state of exactly how we want the rest of them to look. This is mostly a formatting thing, but it also sets up some, like the axes in the figure, that we're going to have to pass on later. So for the animation progression function, for each frame in the animation, we have to have a way of telling func animate what it's going to be. And we do that by progressing a function. So we define a function. I called it update here, but you don't need to. And it has one input variable, which is I. And this is just going to be our time index. So what happens when we pass this to func animate? We pass in the function as an object, and then it knows to iterate through it. So each frame in the animation will be made by progressing this index that we call to it. So the index that we want to progress is the time index. So that's why we have I in here. And we do the exact same thing. We pass in the exact same thing we did for this one with one small change, and it's the color bar. We do not want to add a color bar in our progression one because it will add a color bar on each frame, and the plot will get really tiny and it'll look really funny. It is important to make sure you specify color bar false in this kind of animation. And here we're going to configure the axes again, because this is overriding the axes configurations we make every time. So we're going to reset our axes, and we're also going to set a plot title that includes our progressing time index, just so we can see like the number of what I'm assuming is the day of the year in January plotted as the title of each frame. So we're going to call that, and it's not actually going to run anything because again, we're just defining the function. And here's where we actually make the animation. So when we're using func animation, you always are going to want to save it to an output, whether or not you think you're going to use that output later, because as func animation runs, it has a risk of being collected by Python's garbage collector if it's not saved to an instance. Not super important, just something you need to know. And so in func animation, what we're going to pass is the fig, which is our initial state that we created up there. When I said it doesn't look like we have to use fig, but we need it later, this is where we need it. And then we're going to pass this, the function that we made as an object. And we're going to specify the number of frames, because sometimes stuff can get funky if you don't specify the number of frames that you're going to try and run through this. We know that there's 31 days, and so there's going to be 31 frames in our output. So let's run that. And the next two are going to take a while to run, so I'm going to start them now and then talk about them. This is specific, this next cell right here is specific to show the animation in a Jupyter notebook, which many of you might eventually want to do. We need to set the RC parameter for animation to HTML instead of none. So from here, we're going to import matplotlib. Oh yeah, there it goes. Import matplotlib RC, which stands for RC parameters. And we specify the group and then what element we're altering. So this is automatically set to none. So when you run anim, which is a function animation in the class animation, it doesn't put anything out by default. And so this changes that. So when we have anim, it automatically outputs, like the output of the cell will be an HTML5 video. So this is the animation that we made. You can see it outputs as a little video of 6 seconds long, and we did it, it animates. It's a little clunky looking. It's not very clear, but that's okay. We're gonna fix that in the next step. So here is where we actually save out the animation. As you can see, this is still running. It takes a while. So calling the instance anim again, we do anim.save. And then from here, we specify where we want it to save. We specify the GIF writer that we want to use, which I've specified as pillow here because I've installed it in our Conda environment. And if you hear that, that's my fans picking up, trying to do this. Sorry about that. We specify frames per second equals 5. So each frame is going to run at about 0.2 seconds, which I found to be a standard speed for this. And we're going to specify a higher dots per inch so that the text here and the thing isn't just quite so small, just so we can read it later. And also this will give us a GIF file out so we can use it in other things instead of just an HTML5 video embedded in a Jupyter notebook. So let's see, there we go. So I'm going to open this in the Jupyter notebook, and it's going to look a little funny because this isn't really a file browser, but here we go. This is what we've created. It is so big because it's specified on dots per inch. But as you can see, here is our completed animation. All right, so in summary, matplotlib has animation plotting capacities that can be used with a function and an initial state and called by func animation. But there are many different ways to display animations in Jupyter notebooks, which we did not cover here because there are so many of them. If you're looking for alternate ways, definitely give it a Google. I've just shown you one way here that I think is the easiest. And we've also shown you how to save out GIFs from your created animations. And here are some references below, a link to the gallery and the animation documentation again. All right. So now let's open the second one. This notebook is going to take a little pivot, and we're going to show you some of the current and future planned functionalities of GeoCAT-Viz. The learning objectives for this are to just become familiar with what GeoCAT-Viz is currently and to show you what we plan GeoCAT-Viz to be in the future, and maybe spark some of you to get involved or to think of something that you'd like to see in this in the future. The prerequisites are exactly the same. If you could do the last one, you can do this one. The environment, I should specify the environment we created for this tutorial is a beta version of GeoCAT-Viz. You will not be able to find it in the official releases. Please don't try, it is not polished at all. It was created specifically for this tutorial, just to kind of give you an idea of what stuff in the future is going to be. I will specify when something is a current functionality, a planned functionality, or an eventual functionality, just so you know what's happening when. All right, so we do the imports again. These are the exact same ones as last time. And here are our GeoCAT specific imports. These are ones we're going to use down later and are not currently involved in GeoCAT-Viz. And GeoCAT-Viz util and GVC maps are both currently in GeoCAT-Viz, released fully. You can download them. All right. So our first example in this notebook, if you want to see where we're going here, we're going to use GeoCAT data files again. And this time, you might get another little box. It's totally fine. We're going to pull down this netcdf file, and we're going to specify that we only want one time slice because we're not doing any animation here. All we're doing is we're going to plot a contour plot. So this is actually an example that we have currently in GeoCAT examples plotting gallery. It is NCL color 1 and is the example that we created to kind of do a proof of concept that what I'm going to show you could be a real thing. This cell right here, I'm not going to go through the whole thing because it's large, is how GeoCAT-Viz currently works. This is exactly how we tell you how to do it in GeoCAT examples repository, and is what you can do right now. So we specify the plot, the coastlines, and then we start doing stuff with GeoCAT-Viz utility functions to make it look exactly like NCL. We set axes, limits, and ticks. We set major, minor ticks. We do latitude, longitude tick labels. We use GVC maps to set a color map. We do a bunch of stuff that if you don't really know, if you're not really familiar with GeoCAT, its repositories and GeoCAT-Viz specifically, you might not know these exist and you might not know exactly what's going on, their limitations, how to make them do exactly what you want to do. And that's totally fair. The purpose of these were to recreate as closely as possible NCL style plots. And if you look at some of the examples that we published before we started using these utility functions, it is even messier. So yeah, this is a lot. Let's run it and see what we get. Yeah, there we go. We have a contour plot with a color bar and specified X and Y ticks, a title, and 2 subtitles. And as you might suspect, looking at this plot right here, it doesn't really seem like we'd need this amount of code. And it doesn't require this much code in NCL. You'd be right. There is a lot that goes into making, not displaying the information, but making it look like NCL, which is fair and valid, but maybe not for the everyday user. And so that's where the new functionality of GeoCAT-Viz comes in. The next section is recreating this exact same plot with upcoming GeoCAT-Viz functionality. This is unreleased functionality. It does not currently have a scheduled release date. And if you mess with some of these inputs, it gets very buggy very fast. Yeah, it was created specifically for this tutorial. All right, so let's look at what we have here. This is going to recreate this. We're going to specify a projection and we're going to specify levels, just as we did in the previous section. And then we're going to call contour. This is actually geocat-viz.contourref.contour, but we imported it all the way at the top like this. You can, of course, import it otherwise, but this is how we have it imported here. And we're going to give it a fair level of coargs. We're going to give it the data. We're going to specify the F levels and C levels, the C map, X lim, Y lim, tick marks, projection, and the titles. And look at that. It is the exact same plot. But looking at this, you might be thinking, this is a lot less to think about than all of that. And that's what started this project. This expansion of GeoCAT-Viz is trying to get something that is much more user-friendly and that users would be more inclined to do if they really need an NCL style plot. We are working to further automate a lot of this. We're looking to have our GeoCAT-Viz, we're calling them wrapper functions, estimate or take a guess at what NCL would have done instead of recreating exactly what NCL had done. For example, we're going to do estimation of levels here, so we don't have to explicitly tell it how many levels are in the data, but still giving you the option to if you would like to. We're going to have it try to guess some of the X the X ticks and X limits based on the data you give it. And we're also going to try and have it guess the projection that you're using based on the X array data set that you gave it. So yeah, this is how we're planning on doing contours. I hope you guys are excited about that. And if you would like to see other kind of styles of NCL plots that can be recreated without a lot of bulk and can be created with one of these wrapper functions, definitely let us know if this is something you guys would be interested in. I personally am really proud of it. Yep, that's the summary for that section, and we're going to jump into Taylor diagrams. So Taylor diagrams started with an examples request issue created on GeoCAT examples that asked us to include examples in our plotting gallery of how to create Taylor diagrams. And as we looked into the style of plot, it became very clear very fast that there isn't a good way to do this using vanilla matplotlib from a user who just wants to make a plot and not dive into exactly how matplotlib works and why. If you're anything like me, maybe you didn't know what a Taylor diagram was. So let's do a little Taylor diagram primer. Taylor diagrams are, quote, a concise statistical summary of how well patterns match each other in terms of their correlation, their root mean squared difference, and the ratio of their differences, according to the original AGU paper published by Taylor in 2001. This is just the abstract from that paper. And here's a link to it if you'd like to read more information about it. He also published in 2005 kind of like a, this is what Taylor diagrams are in a less formal setting, if you want to go and find that too. All right, so here's an example of a Taylor diagram. I am not an expert in Taylor diagrams, but if you look at this, I wouldn't know how to plot that. I didn't know how to plot that in Matplotlib. There's a curved axis that has stuff going on. I'm not exactly sure what the coordinate system is doing. There's like circular lines and an unusual style of label here. But we got into it. So what we needed to do is get the normalized root mean square differences and a bias statistic and a centered pattern correlation. And from that, you can create this. And so here's what we have done. This is recreating one of NCL's plots that I think it's Taylor 3, if I believe, and will be released when the Taylor diagrams get released, hopefully, on GeoCAT-Viz. This is planned for release in September, if you want to look for that. And so this is an example of how you will be able to use that in September. So we're going to recreate this exact one, which is from NCL in Python. So we're going to specify case A and case B up here. Taylor diagrams in NCL assume that you already have these calculated with a package called Taylor statistics, but the statistics are not that hard to compute. And so ours also assumes that you have pre-computed them. So we're going to specify case A ratio, which is case variance divided by the case or the reference variance, and case A cross correlation coefficient of case to reference. And we're going to do the same thing for case B. And this was all pre-computed. And now this is where GeoCAT-Viz comes in. We're going to specify Taylor plot is TP, and we're going to create a Taylor diagram instance, which is called Taylor diagram, which we imported the same way as contour after the previous example. And from this, we're going to add both of the models separately with an add model set call. We're at the ratio, the cross correlation coefficient. We're going to make this one red, have O markers, and label it case A. And we're going to do the exact same thing for case B. To get the unstandard label down here, what we're going to do is we're going to specify model names for each set of these points. And we're going to add it to the Taylor diagram instance with the add model name and just pass it that name array. And by calling add legend on the Taylor diagram instance, we're going to add all of this information as a legend to the Taylor diagram. And then this is just going to show us the plot. And that's what we created. It's a pretty good estimation of what we had. Here's a direct comparison. Here's the original NCL, and here's the GeoCAT-Viz recreation, which are the same exact plots we just created above, just side by side, so you can look at them easier. They look pretty close. You might notice slight differences. For instance, there's sub tick marks between 0.9 and 0.99 here that we have not yet been able to recreate in Taylor. And we're really looking for information on what scientists who use Taylor diagrams need out of our Taylor diagram functionality. Additional features that are in NCL Taylor diagrams are also planned for these Taylor diagrams. We're releasing a whole host of examples that we've recreated, not just this one. Ones that add radial grid lines here and additional reference lines. And we're really, really excited about this development. In summary, GeoCAT is working on more user-friendly ways to recreate NCL style plots, both for functionality that is recreatable in Python and some that is not, like Taylor diagrams. Here's the link to the GeoCAT-Viz repository where you can make requests or comment on what we're doing, see the work in progress for both Taylor diagrams and Contour. And here is something that we've created specifically for use starting after these tutorials, which is a feature request form for users that might not be as comfortable using GeoCAT or using, GitHub issues, but still would like a way to request features to the team. You can also contact the team at geocat@ucar.edu or by contacting any one of the members individually, and we'll pass on to the team. We really, really want to hear from you. And a special thanks to this year's SciPlex interns, Aaron Lincoln and Jackie Lee, who took basically the entire second notebook to a proof of concept that the GeoCAT team had kind of set aside to a nearly completed features that we can add to GeoCAT-Viz. All right, so that's it for the demo part of this tutorial. Let's go back to the slides. Oh dear, wrong link. Yeah, okay. So do you have something to contribute? I just said a lot of this, but here's specific links. Links to these slides will be sent out so you can follow them there. Check out our contributors guide if you want to write something yourself and have it included in GeoCAT, definitely check that out. Or open an issue if you want us to add something. Or again, here's another link to the feature request form. It's just a Google form. You don't even have to give your name, just a brief description of what you want and links to any other implementations that you might have found. So are there any questions? I see chat's been kind of going. I'll pull that up now. Let's see. Also, I don't know how many of you are here, but if one of you wants to unmute yourself and ask a question directly while I try and read through what's happening in chat, that's totally fine.
I think one question that wasn't answered in the chat was from Simone about whether this works with irregular grids.
It does not yet. It is limited, especially, I'm assuming you're talking about Contour. The Contour plotting capabilities are the same as the Contour plotting capabilities in what already existed in Viz. It is mostly just a wrapper function that allows users to access NCL style plots more quickly, not one that adds any sort of unstructured grids functionality. Does that answer your question? Will this be added later? Yes. Well, I shouldn't say yes. GeoCAT is planning on doing some work on unstructured grids, and I don't know if it'll be added to GeoCAT-Viz functionality, but we'll see. I'm not sure how to answer that question. I'm sorry.
Yeah, I threw in the chat there.
Yes,
I put a blog post together a couple weeks ago, working with unstructured CSM data, and kind of walked through some of the nuances worth working with unstructured grids, and it's like an interactive plot. So if anyone's interested in that, I put that there. But yeah, this would be great to incorporate into the GeoCAT-Viz repository. So.
Yeah, definitely. Yeah, GeoCAT-Viz as it is isn't isn't really adding new functionality to contour plots, but we'll look into that. I'm seeing, does GeoCAT graphics sit entirely on Matplot? Yeah, it does. Everything underneath the hood is Matplotlib, and a lot of times, like anything that you would do with Matplotlib, for example, like if you create a plot, you can still edit the plot like you would a Matplotlib plot, is our intention. You can pass in quargs that aren't GeoCAT specific, but will then be passed on to Matplotlib and returned out to you. So any like additional like visualization functionality that we're kind of hiding in the back end, it's still entirely like editable by the end user, if that makes sense. How many grid points were displayed in the animation? It's not a ton of data points. I think this was pretty small. As you saw, the last step took a while to run, even with a small data set. I think it was something by like 30 by 60 on latitude, longitude, and 31 time slices. So extremely not a big data kind of issue. I'm not exactly sure how you would handle something if it got that big. I think there's ways that you can use threading on some of it, but that is not currently an example in GeoCAT examples. How would you create PS plots and download them? You can specify the type of plot. I saved it out as like a GIF, but you can save it out as other kinds of plots too, if that's what you're talking about. Yeah, I see your comment. Thank you, John Klein. The GeoCAT team has been funded to add visualization and analysis routines for unstructured grid data. The project is called Project Regen, which will kick off in September. Stay tuned. Yes, currently not something until that kicks off that we are looking to add, but it's in the works to add this kind of thing. How are you making decisions about what to reproduce from NCL and what not to? As it is easy in Matplot. What new plot features are you doing? Just interested. So the features of what to exactly reproduce in NCL, I think this started off, the hackathon that I mentioned was before I started here, but there was kind of a desire to show that Python could recreate anything that NCL could do, like visually. And that has persisted in our GeoCAT examples repository. A lot of what we show in GeoCAT examples is not examples of how, like strictly the purpose of how to plot in Matplotlib, but how to recreate NCL in Matplotlib, which is a slightly different goal. What we choose to add is basically just kind of, especially in Contour, the look and feel of what NCL would have done. Kind of, you know how the package you might be familiar with, Seaborn, how it sits on top of Matplotlib and it produced Seaborn style plots. Some of what we're aiming to do with the new GeoCAT-Viz functionality is kind of do the same thing, but for NCL style plots, that something that sits on top of Matplotlib and is geared towards users who may be more familiar with NCL or want to create that style of plot, or is just more fine-tuned to geoscience data. As far as new plot features, we'd really like to hear from you guys. We're not atmospheric scientists on this team. We need to know what you guys want. As I said, the Taylor diagrams was something that was requested, and it was one of the first things that we decided to do. Yes, is GeoCAT compatible with older versions of Python, like greater than 3.0? Is there dependency issues that a user should be aware of? Currently, GeoCAT-Viz, this demo is only compatible with this demo. We just dropped support for Python 3.6, but it is available for Python 3.7 through 3.9 currently. All the packages are, and some of them work better on Mac or Linux than on Windows. I think GeoCAT-Viz, before the most recent release was platform independent, as is several other of the repositories, but we are working on making it available on a broader host of Python greater than 3.7 setups. Interactive capabilities. We're not currently looking at those, but I do. It's like really low on my like to-do list every week that I will probably eventually get around to. I would love to create some sort of examples that show interactive plots. I'm not sure GeoCAT examples is the place where that would be, because NCL didn't really have interactive plots, but I would love to add that functionality at some point. I think it's really cool and really useful. Let's see. I would say, oh, that's not a question. But yes, that's true. GeoCAT-Viz is less efficient than NCL because NCL might be using the default parameters, and Python equivalent examples have extra lines of code to change parameters to match NCL. So yeah, absolutely. NCL does make stuff in less lines of code, but sometimes you might want to do things in Python, possibly, instead of using NCL. But also that is part of what we're trying to address with GeoCAT-Viz, is to make the length of GeoCAT-Viz scripts and GeoCAT example scripts more closely match what you would have had to do in NCL. Let's see, is it easy to animate with panels? Panels being a Matplotlib artist thing, if I'm... Yeah, yeah. So actually, the other type of animation that I didn't really talk about here, and I'm not nearly as familiar with, is function artist. And so I believe that's what you'd want to go with if you're going to want to animate Matplotlib artists instead of using like a function. Also, the functions that you see in examples, the function animations and examples that you're most likely to see on the internet are things like not exactly two-dimensional data, if that makes sense. We kind of had to figure out how to adapt this to create kind of just data which moves through. A lot of them are like replacing something else, or they're, instead of an index that's being passed through the update or progression function, it's something else like a variable that then like shows the progression of like a trend or something over time, if that makes sense. Yeah, for the contour plot, the plot.save, contour.ps, writer pillow, I don't totally know. I will look into that. I'm not sure how to save those plots out. I've never done one before, but you can write out different types of plots. I do know that. I will look into that. Let me make a note. Attribute error. Matplotlib pyplot. You might want to try the save fig instead of just save. If you're calling it on plt.save. So if you're going to do it off of matplotlib.pyplot, you actually have to do save fig, not save. You can call save on func animation though. Yeah, I don't know why it's called different. I'm still not sure if it would work for PS plots though. I will look into that. Let me make a note. All right. Can you run these scripts on Cheyenne or Casper without the notebook? I guess that would depend on which script you're asking about. The first notebook, absolutely. That will, as far as I know, work on both Cheyenne and Casper. The second script, it will not work now just because the release, actually it might, I shouldn't say that. It might. The beta release of GeoCAT-Viz might prevent you from doing that. I have not tested any of this on those, but stuff generally works better between like Casper and Cheyenne and Mac than like Windows would. As yeah, Cartify sometimes that's finicky on Cheyenne because that's to download. Yeah, it does. Thank you, Julia. I'm not totally sure. Do you need to load special libraries? For this one, the beta release of GeoCAT-Viz is installed with pip, but for normally you can install all of GeoCAT, all of GeoCAT's packages with Conda, which if you're already using Conda, you just specify the NCAR channel, and then it should be able to get them all, if that's what you mean by special libraries. I have run, I think maybe all of GeoCAT's packages on Casper. If libraries related to GeoCAT, yeah, I have run GeoCAT on Casper before, and it worked fine. It's just it's a Conda install. Yeah, of course. Let's see. Are there any more questions?
Okay, thank you, Anissa. Can everyone flood the chat with your gratitude and maybe something you learned today? And we will see you all in 2 weeks, September 8th, I believe, the second Wednesday in September, where Leah Kutz will cover GeoCAT Comp. So that'll be a little bit of a continuation from this week in terms of highlighting the GeoCAT team and some functions that play well together. Okay, thanks a lot.
Thanks for having me.
Okay.